Let's talk about some of the details of the frictional force for a little bit. Friction depends on two things, the materials factor and the force pressing two surfaces together. So the one thing to remember about friction is it always keeps or always acts to keep two surfaces or materials from slipping or sliding past each other. For example, what I mean by two materials or two surfaces, think of rubber tires on an asphalt road. Okay, right, gravel and coated in tar and laid down and packed hard. Those two materials are what make friction what it is for those things. That's why tires have such a high amount of friction on the road, is because of the way the tires are made and the way the asphalt is made. And when those things try to slide or rub past each other, like your hand sliding over each other, you get a different amount of friction. It doesn't make any sense to say, what is the amount of friction of a rubber tire? Well, that's a very difficult question to answer. It matters what surface is the rubber tire on. Is the rubber tire on asphalt? Is it on gravel? Is it on grass or mud or ice or snow? Right? So it's always two materials together that kind of make friction and contribute to friction. It's never just one material all by itself. When the materials try to slide past each other, little bumps and ridges, little unevennesses in the surface, rub against each other and create friction. So the materials factor, let's talk about that just for a second. The materials factor is kind of thinking of, as kind of like a stickiness factor. It's how sticky are two materials when they're together, okay, when they try to rub or slide past each other. Think of a common example, think of Velcro. You put two pieces of Velcro together and try to pull them apart, not the normal way, okay, but try to pull them apart by keeping one flat and sliding the other one flat off of it. Very difficult to do. A great deal of friction in that case, because those two things are made to grab and really stick together. Or think of pushing a desk across the floor. The little plastic feet on the bottom of the desk and the hard tile surface of the floor don't really stick together all that well, so it's relatively easy to move the desk around. So the stickiness factor is kind of how well those two materials want to stick together, or how much they want to stick together. This materials factor is frequently less than 1. All right, and it opposes slipping or sliding, as we've already talked about. It's a number that tells us how well the two things stick together. So, for example, steel on steel, okay, dry steel on dry steel, has quite a bit of friction. Its stickiness factor might be in the 0.6 to 0.7 range. If we add oil in between those surfaces, right, so that now each surface is sliding against oil, then that factor may drop down to 0.1 or 0.2. The stickiness factor, this materials factor, is determined experimentally. So we like, say, for dragging a desk across the floor, we would tie a rope around the desk or on the desk somehow, attach a spring scale to it, and start pulling. You pull very gently at first and pull a little bit harder and gradually increase how hard you're pulling until at some point the desk would begin to move. By reading the scale carefully, we can figure out how much friction there was acting on the desk at the moment it began to move. That allows us then to figure out the stickiness factor. Take the desk to a new area, say out on a cement sidewalk, and do the same thing. You would get a different value for friction because the little plastic feet on the desk and cement have a different stickiness value or materials factor than the little plastic feet and the tile of the floor do. So the different materials make a big difference there. So this materials factor has to be determined experimentally or given. The symbol for the stickiness factor that we use is mu. Okay, it's a lowercase Greek letter. It's written by kind of starting down here low and making a U shape. Okay, but it has this little extra tail on the side. The name is the coefficient of friction. And the units are none. There are no units to this materials factor. It's just a number, just as a multiplier that tells us when we put these two things together. So a steel ice skate blade on ice would have a very low coefficient of friction, right? The ice skate slides very easily across the ice, so the coefficient of friction would be very low, 0.1, 0.07, okay, something quite low. Rock climbing shoes, something designed to help you get a lot of grip so you can climb up rock surfaces, would have a very high stickiness factor, possibly even larger than 1 in that example, because the materials the shoes are made out of, the way in which they're manufactured, are made to grip or be very sticky with most surfaces, but the rock surfaces that rock climbers climb primarily one of those surfaces. The other is this pressing force. How hard the two surfaces are pressed together. You can do this with your hands. If you take your hands and put them together very gently and rub, it's very easy. You can feel the friction in the palms of your hands. You can feel the rubbing, the friction, but it's very simple to do, very easy. If you press them a little harder together, it's more difficult to rub. And if you press them very tightly together, you can press them so tightly together that it's nearly impossible to make your hands move. Okay, so how hard you press them together is a factor in how much friction there is, and this is just the normal force, okay, the common normal force that we've been talking about, and it is determined in all the usual ways. So force diagrams, sine and cosine, trigonometry, solving equations with Newton's first law or second law. Okay, so it's just the normal, this pressing force is just the normal force, and you just determine that using the normal, the common ways that we've been talking about. The equation then is that frictional force is equal to the materials factor multiplied by the pressing force, or the normal force. So F equals mu times N, or Fn is the equation that we often get. N standing for the normal force, so friction, materials, and normal. So a couple of examples that we could possibly work through. I had these written out earlier. There we go. So this first example, I've got an object, a box. I usually use boxes for most of my examples because I'm really a lousy artist. And I don't draw people or dogs or cats or cars or more interesting things very well. So imagine this to be whatever you want it to be. Let's say it's moving to the right, it's sliding to the right, and so friction would be acting to prevent sliding. The normal force points upwards, the gravity force points downwards. I can see from the diagram that the normal force and gravity force have to be balanced. Friction's probably making this object slow down if it's sliding to the right. The mass is 70 kilograms. This materials factor, mu, is 0.52, and want to determine the frictional force. So we'll use our new equation. Since I know what mu is, my new equation will be great. So friction equals mu times the normal force. Given is the mu value, 0.52, and the normal force is going to just be balanced with gravity, so it'll have the same value. So if gravity is 700 newtons, the normal force will be 700 newtons. I know the gravity force is 700 newtons because the mass is 70 kilograms multiplied by 10. Substitute those numbers into the equation, and friction equals 364 newtons. That's the amount of frictional force acting on this block in this example. Another example might be to look at this box, and we're told that it's moving. It's accelerating actually to the right with these given values. Mass of 15 kilograms. The applied force here is being pulled is 75 newtons. It accelerates 1.4 meters per second squared, so the applied force has to be bigger than friction. We want to determine friction and mu. My new equation won't work very well in this example because I don't know either of these two numbers, okay, both of which are in my equation, and so I can't solve yet. I can, however, find the frictional force using Newton's second law that we've been talking about a lot. I'll visualize this as go minus stop. The force making the box go is the applied force. The force making the box stop is friction. Those two are at odds with each other. And so my equation becomes go minus stop equals ma, or applied force minus friction equals mass times acceleration. Plugging in given values, I get 75 newtons minus friction equals 15 times 1.4. 15 times 1.4 is 21 when I multiply that out. And so solving that equation gives me friction equal to 54 newtons. I'll pause for a second, let you kind of look at those numbers, or maybe you can pause for a second and make sure you get that same answer. When you're ready, restart the video. To find the mu value now that I need to find, I'll use my new equation. So friction I just determined is 54 newtons. The normal force, again looking back at the diagram, the normal force has to balance gravity, so Fg will be 150 newtons. So Fn will be 150 newtons. Solving the equation, mu equals friction divided by Fn. Friction is 54 newtons. Normal force is 150 newtons. Dividing those numbers gives you 0.36 for mu. There are no units on mu. It's just a multiplier. It's just a number without units. Hopefully that helps a little bit. Good luck on your homework.